I loved slides as a kid, but frankly, I always thought that the slides had way too high of a coefficient of friction. You know what I mean, right? You try to slide, but you don't even move. So here's what I did. You go to your standard fast food restaurant and you get one of those plastic trays that you put your food on. Ride the slide down on that thing. The plastic on plastic has almost no friction and you fly. It's amazing. Now, I would tell you not to try this at home, but given that you're in high school, I bet you can't fit into the slides. Anyway, the point is, you're cruising down this slide really fast. And if we want to think about friction or acceleration in this context, it's actually a little complicated because you're on a slope. And when we do physics on a slope, we have to think about that really carefully. That's called an inclined plane, this slope thing. And in this lesson, we're going to learn all about doing physics on an inclined plane. Let's do it. Let's review our lesson objectives. First, you'll learn to split up acceleration into two components. This is very similar to what we did in our lessons on projectile motions and kinematics. And so we'll see here, you can just split up acceleration into two components. Then we'll learn to calculate the normal force on a slope. And there you'll see that when we have the two components of acceleration, one of them is going to give us info about the normal force. If it feels a little confusing at the moment, that's okay. These are much clearer once we have a picture. Then we'll practice solving problems on an inclined plane, which is just a fancy name for a slope. Let's start by thinking about acceleration. What is accelerating the skier down the slope? Again, remember, also an inclined plane. Well, the answer seems kind of obvious, gravity. But the interesting thing about being on a slope is that gravity does two things at the same time. One, it holds us down to the surface. And two, it accelerates us down the hill. So it's quite natural to think about gravity as having two components on a slope. To think more about this, let's answer a question about a skier. If friction is neglected, how quickly is the skier accelerated downhill on a 35-degree slope? And remember, here we have a sloped surface, and just like I've already referenced, in physics we call these sloped surfaces an inclined plane. In physics, we call a sloped surface an inclined plane. And the interesting thing about an inclined plane is that gravity pulls straight down towards the center of the Earth. And if we want to think about the acceleration of the skier, well, it's quite natural to split that into two components. One is the acceleration parallel to the surface, and so there we use those two parallel lines next to A to indicate that we're talking about the acceleration parallel to the surface. That's what makes you go fast when you're skiing. And then the acceleration perpendicular to the surface. So there we use the subscript of that little perpendicular sign, and that's the acceleration that holds the skier down onto the slope. And all of this we can think about basically as occurring on a triangle. It's like our skier is chilling out on a triangle. And if we know the theta, the degree sign there for our triangle, we can actually calculate those two different components of acceleration. It turns out that the perpendicular acceleration is equal to g, that's the acceleration due to gravity, times cosine theta. Of course, this is assuming your inclined plane is on the surface of the Earth, but that's pretty usual, I suppose. And if we want to calculate the acceleration parallel to the surface, that's g sine theta. So I recommend writing these two equations down. You're going to use them over and over again in these inclined plane problems, and it's good to just kind of commit them to memory. So remember that the perpendicular one uses cosine and the parallel one uses sine. All right, let's go back to our problem now. It says if friction is neglected, how quickly is the skier accelerated downhill? Well, this is asking us about the parallel acceleration. And so for the parallel acceleration, we just have to remember that it's equal to g sine theta. For g, I'm going to plug in 9.8 because that's the acceleration due to gravity on Earth. And then for the degrees, I'm going to plug in 35 because that's the degrees of the slope. Okay, so when we do that, we're going to get a parallel acceleration of 5.621 and some other decimals meters per second squared. That's always the units for acceleration, right? Meters per second squared. We want to round now to 2 sig figs because our 35-degree slope has 2 sig figs. And because we have a 2 there, we're going to round down to 5.6. So we have 5.6 meters per second squared. Okay, now that we've done this parallel acceleration, let's take a look at actually the forces on this surface. So this question says, what is the normal force of the skier on a 35-degree slope if they have a mass of 55 kilograms? Well, just as we can split up the acceleration into components, we can split up the force of gravity into components. So we have the force of gravity that's parallel to the surface, drawing that skier down the hill at a rapid speed, and the force of gravity that's perpendicular to the surface, that is holding the skier to the slope. Now remember, the normal force is perpendicular to the surface. Okay, so when we think about which one of these forces we want to use to calculate the normal force, it's going to be the perpendicular one. Here you can see the normal force drawn as a black arrow that's pointing opposite of the perpendicular force, and those are equal and opposite. So we can say that their magnitudes are equal. The magnitude of the normal force is equal to the magnitude of that perpendicular force there. Okay, so to solve this problem, we're going to start with that relationship, that the normal force is equal to the perpendicular force. All right, well, how do we calculate the perpendicular force? Well, remember that force is always just mass times acceleration from Newton's second law. And so here we're going to use mass times acceleration, but the acceleration that's relevant is the perpendicular acceleration. So now we know that the normal force is equal to the mass times the perpendicular acceleration. Okay, then we have to remind ourselves of how to calculate that perpendicular acceleration. Did you write it down? If so, you'll remember that it's A equals G cosine theta. And so we'll just substitute in that G cosine theta into my perpendicular acceleration, and we'll get that the normal force is equal to mass times gravity times cosine theta. Okay, well, at this point, we're ready to plug in all the numbers we know there. For mass, we have 55 kilograms, that's the mass of the skier. For gravity, we have 9.8 meters per second squared. And then we plug in 35 degrees, again, for the slope that the skier is on. That's going to give us a normal force of 441.52 newtons. And again, if we round to 2 sig figs, we'll keep those first 2 4s, and we'll get 440 newtons. This problem tells us that a girl with a mass of 18 kilograms goes down a slide with a 21-degree slope. What is her acceleration if friction is neglected? Well, let's start with a picture. We know that we have a slide here, and that the angle is about 21 degrees. Let's draw the girl on the slide. Oh, it's such a cute little girl. Okay, it's a box. In any case, the acceleration we want to find is this one. Remember that gravity is straight down. So that's our gravity right there. And so what we're actually finding is the acceleration parallel to the slide surface. That's acceleration parallel. And remember that the parallel acceleration is equal to G sine theta. So we know G sine theta is equal to the parallel acceleration. All we need to do then is grab G, which is 9.8 meters per second squared, sine 21 degrees. Now, we can plug that into our calculator. Just a quick reminder, make sure your calculator is in degree mode. Okay, so when we plug that in, we should get 3.51 and then some more digits. If you didn't get that, double check that your calculator is in degree mode. You can Google the specific model of your calculator and how to change it to degree mode if you get stuck. We need to round to 2 sig figs because the 9.8 has 1 sig figs and the 21 has 1 sig figs. So 2 sig figs here would be the 3 and the 5. So we'll round our parallel acceleration to 3.5 meters per second squared. And that's the parallel acceleration. That's the acceleration of the girl down the slide if we neglect friction. This problem builds just a little bit in complexity from our last problem. Here we have a girl with a mass of 18 kilograms, same girl, going down a slide with a 21-degree slope, same slide. Find the coefficient of kinetic friction if the friction is known to be 22 newtons. So a new wrinkle here. Now we're looking for the coefficient of kinetic friction. Here we'll start by writing down the force for kinetic friction, which we know is equal to F equals mu k n, where n is the normal force. Now, let's list the variables we do know. We were told what the force of friction is. It's 22 newtons. We were also told what the mass of the girl was, and we know that's 18 kilograms. We know what theta is for our slide, and that's 21 degrees. And what we're looking for here is mu k. We're looking for the kinetic coefficient of friction. That's what that little weird mu is. Now, what you might realize if we look at this equation is we have F, good, but we don't have mu k and we don't have n. We don't know either of those. And so we're going to have to do a little work before we can use our friction equation. We need to find what the normal force is. Here we're going to apply our video knowledge, the knowledge we just learned, to solve for that normal force. Remember that the normal force, the magnitude of it, that means we're not going to worry about the direction, we're just thinking about the size of it, is equal to the magnitude of the force perpendicular to our surface. So this is the force perpendicular to the slide, basically how hard that girl is being pressed down into the slide. And now remember that we can plug in for our force mass times acceleration. So we know that the normal force is equal to mass times acceleration. But it's not just any old acceleration, it's acceleration in the perpendicular direction. And that's because we're looking at the force in the perpendicular direction. And so that means that the normal force is equal to mass times acceleration in the perpendicular direction. We know acceleration in the perpendicular direction is equal to g cosine theta. So we can just plug in g cosine theta for that acceleration in the perpendicular direction. All right, now we have an equation that will solve for our normal force. We know then that our normal force is equal to mass, that's 18, times acceleration, that's 9.8, times cosine of our degrees, which is 21. So that makes our normal force equal to 164 point a bunch of decimals. We're going to ignore those decimals for a second. We'll round at the very end, okay? So what we have then is now the normal force. We know what that's equal to. The normal force is 164 something newtons. Now we're ready to go ahead and use our force equation because now we have the normal force and the force of friction. We can plug in the normal force, which we know is going to be the 164, and the force of friction, which we know is the 22 newtons. So that means we'll write 22 equals mu k times our 164. And here I'll add the two decimal places, 0.68. In a second, we'll round for sig figs at our final answer. How do we solve for the coefficient of kinetic friction? Well, all we need to do is divide both sides by that 164.68. So we'll divide both sides by the 164.68. Now, once we do that, we're going to get that mu k is equal to 22 divided by 164.68. That gives us 0.1335 and a bunch of other decimals. How many sig figs do we have? Well, just like in the last problem, our force and our mass and our angle all have 2 sig figs, and so we'll round that to 2 sig figs, which would be 0.13. And remember, the coefficient of kinetic friction is unitless. So that would be the coefficient of kinetic friction on this girl traveling down the slide. Let's review what we've learned. We learned to split up acceleration into 2 components, the acceleration parallel to an inclined plane and the acceleration perpendicular to that inclined plane. Then we learned to calculate the normal force on a slope where we saw that it's just equal and opposite to that perpendicular force. And lastly, we practiced solving problems on an inclined plane so you get really good at this stuff.
Hey, hey.